So we are in our systems approach. This is week 1 and 4th lecture. Why we are spending 2 or 3 lectures on this is because for PHM to implement, we require a systems approach, because PHM is a resource intensive option. So it cannot be applied anywhere. That is number 1, and number 2, still R&D is going on in this field. Only candidate component will be the one where the technology has matured actually. So now we have seen in previous lecture probabilistic risk assessment, which offers us to develop a risk-based engineering, and risk-based engineering then it becomes a central tool where different applications can be developed. So the first application is risk conscious operation management. So in this lecture we will see how risk-based engineering, what are the major elements, and how it has evolved into risk conscious operation management. Why operation management? Actually it is operation and maintenance management, because PHM is directly linked to the maintenance ecosystem. So that's why we are taking this route to understand or implement the systems approach. So the traditional approach, deterministic, we can have maybe a couple of slides on this, but deterministic is a traditional approach where we design the system using stress, strength, and then factor of safety, and then whether deliverables can be there, different size, configuration, okay, and then the next is probabilistic risk assessment. So now we are trying to see the role of PRA in risk-based engineering, and finally then we have to understand how risk is characterized. One matrix we have given the core damage frequency, but there are other elements involved. So we will discuss in this lecture. And risk conscious operation management, because risk conscious operation management is built on risk-based engineering, okay, and risk-based engineering in turn is built on probabilistic risk assessment and deterministic safety assessment. Then we will understand the requirement. So this is my book, Risk-Based Engineering, published in 2018, and it provides all the details. It is available on Amazon in open domain. You can have it. So myself and Professor Michael Pett from Center for Advanced Life Cycle Engineering, University of Maryland, we too have worked on it, and it is published by Springer in 2018. But I will provide here the essential features only, whatever required in the context of implementing PHM. So let us see, first of all, either we call integrated risk-based engineering or risk-based engineering, both are same. What are the application? So in design, it is the site selection, optimization, validation and verification, uncertainty, evaluation. So because earlier the concept of factor of safety was there, where the factor of 2, 3 and all they were provided, but here now we got a very rational based approach for uncertainty characterization. So since you have a model of the plant, a design optimization can be done and validation can also be done, including the failure criteria for individual systems and all that, and whether it is meeting the probabilistic targets, you know. And during operation, it is decision making, like as I mentioned, technical specification is the central document that ensures safety of the plant, and it cannot be it should not be violated. But tech spec, as of the traditional approach for tech spec structuring was based on either experience or expert opinion or vendor specifications. Okay, as far as the plant parameters are concerned, they come from like some core temperature and all those things. They come from lot of simulations or testing that has to be done. So that's how but then since the PRA provides a very quantified and rational based matrix, there is a trend internationally world over that plant technical specification, especially the allowable outage time for a component in the system in a plant or surveillance interval of various components. So these two things are very well being addressed. In fact, some of the plants are even addressing the staffing requirements. So like that, PRA becomes a very risk-based approach, becomes a very useful when we are talking about tech spec optimization. Then development and optimization of normal and emergency operating procedure. It is very easy because human factor is a part of this. So it is easy to optimize the procedure, especially the emergency operating procedure, and training thing also. So like training, how it is important to understand what is the impact of simulator on training program. So like that, these studies can be done over there. Then in regulation, it forms part of risk informed decision making, oversight and compliance, life extension and requalification. So in fact, now PRA or risk-based risk-informed approach has become part of the regulation compliance and all procedures. Plant aging. If the plant has aged, identification, optimization. In aging, this model, PRA model are being used because it has got a performance integrated into the model itself. So a decision can be taken about remaining useful life or the component repair or overall activity, whether it has to be repaired or it is to be replaced or it is to be refurbished. This kind of decision can be taken in the plant. So risk-based engineering has become, but then our subject is risk-conscious operations management. So because we are talking about the maintenance chart which has been maintenance or surveillance chart which has been given, we want to see how PHM can impact that thing. So now risk-conscious operation management operates in this domain. So risk is appearing this as a central figure in this. So how risk characterization can be done? This is one very simple and elegant figure. Here you can see how risk can be characterized. So plant data and information, and then you have to ask what can go wrong, how frequently it can, that is frequency. It can happen, it could be qualitative, it can be quantitative, but once PRA is there, we have to use quantified estimate, and then we have a likelihood of accidents. Okay. Then what are the hazards potential of the plant? These two together, if we have, the risk from the plant can be estimated. So here we have consequences, here we have likelihood and the accidents. So and the same philosophy has been implemented in probabilistic risk assessment. We have a quantification of the likelihood or probability of the accident, how it can happen, how frequently it can happen, and what is the hazard potential, and that gives a level of core damage frequency risk from the plant. So consequences, likelihood together, and that's how the definition is risk. Risk is nothing but 1 to n sequence, likelihood I into consequences I. So that like there are thousands of the sequences, or maybe more than tens of thousands sequences are there. They have to add a summation of this thing, and that will give you a risk from the plant. Now this we are talking about the safety risk. But again, another angle has come, that is safety. Along with the safety risk, security risk are to be are the overriding factor. Okay, because in the new context, now we have to analyze the security scenario also, and it should not lead to the accident, and or something should not happen in the operation and maintenance that lead to the scenario, and that is again like a probabilistic risk assessment. Probabilistic security risk assessment has to be performed. It could be security risk assessment deterministic way also, and finally you have to evaluate what are the chances, what are the mitigation, internal security, external security risk, internal and external together, malicious this thing aspect has to be analyzed. There is an international level recognition of safety, or conversely speaking, risk conscious percolating down to institution to plant managed to grassroots level. So it is a risk conscious ecosystem which from top to down bottom it gets translated, and that's why we can say risk conscious culture. An integrated model employing deterministic and probabilistic approach provides an holistic and rational based, more realistic framework actually. the target should be, now these targets are coming somewhere in black and white, sometimes they are coming as an example. The member of public should be exposed to 1 into 10 to the power minus 6 or 1 into 10 to the power less than 1 into 6 or 10 to the power 7. New plants are being built with 1 into 10 to the power minus 7 per year, that frequency or less frequency. So this can be another matrix which can characterize advancement in technology, because the exceedent frequencies are like simple case, a small modular reactor is there, they are being built world over. Now for them the risk level should be less than 10 to the power minus 7 per year in the public domain. Okay. So then it is for everyone to understand, okay, risk levels are low given the configuration, because they are using a lot of passive features, they are using low inventory for power, and they are basically, their structure wise it is such that the public the area, rather public area will be there or not, that again a debate is going on. So this kind of things can be handled when we have quantified estimates available. If I look at the integrated risk-based approach, this is the framework here, where we have, suppose if some decision has to be taken in a plant, or a plant has to be built, like you are building an SMR. So you will provide a deterministic analysis, you will provide a probabilistic analysis, and then we have integrated risk assessment, okay, together, and then validation and deterministic and probabilistic goals. There are written goals, there are sometimes we have to formulate goal at national level and international level, but goals are available, and then we have to have enhanced monitoring and surveillance PHM, its impact, okay, and then safety and whether they are reducing safety and again meeting the availability target also. So if that is everything is yes, induction is integral to the system, and there are many risk conscious operation management. These are the this can put to use for ARCOM, operation scenario ecosystem. If they are not meeting the goal, the redefine the goal, or rethink about it, what are the weakness over here and all, again come back to it. So it's a closed loop exercise actually. So this is a very elaborate and robust model for implementing integrated risk-based engineering approach. And then when you translate that, so how from PRA, it is translating, we had a PRA. So PRA should have these attributes. Desired attributes are quantification, integration, and attributes with uncertainty characterization and acceptable level of uncertainty. Integration should be level that most of the plant component which affect the system, and to the quantification level, they should be there. Rational based approach is there, because fault-free inventory, they provide a line diagram or graphical approach where at any component type you can think about it, if and then. If this happens, what happens? If this figure is low, how? You can do a simulation in a plant simulator, or you can do a simulator where in a risk monitor and see the impact actually. So this provides a holistic framework. This is the role of PR, and the human factor integration, it is one of the challenge to have a human reliability data with acceptable level of uncertainty. Presently, the observation is that human factors carries more uncertainty compared to hardware components, and that's why in risk-based engineering there is a model called probabilistic C-cube model has been developed, and there it doesn't take care of only random failures, it takes care of malicious or security related failure. So one C is C-cube means consciousness, cognition, and conscience. So conscience is a factor which takes care of security obligation, and then various applications are there, reviews are there, and then elegant framework. It's an elegant framework. It is accepted fact now that PRA provides a very, and since it is performed at 3 level, at 3rd level it can become a part of the emergency procedure also. Then again quantification is the one of the attribute that we have discussed. From there we got risk-based engineering, we saw last slide, and now it is basic spin-off of risk-based engineering could be for maintenance operation, it could be for design, it could be for site selection. So one first application that has been developed is ARCOM, that is risk conscious operation management and maintenance management. So now risk conscious operation management, a model. What is this model actually? Okay, and the second book that I have written is on is published is myself in 2023. So this book discusses operational aspect and maintenance aspect. Actually, sometimes maintenance is not spelled out separately, so it becomes part of operations. Okay, risk conscious operations and management. Okay, and now what is happening is we have risk based engineering approach here. We have a nuclear plant and the plant configuration and reliability data that gives us to make risk conscious risk based engineering approach. So from here we have risk insight, okay, in risk conscious culture. And what is our consciousness protocol? That is human reliability data and methods and human and organizational factor. There are some individual organizational factors which are there, protocol is there, which will tell us what is the risk conscious culture. Along with the CQB model, we have this input and risk input comes here, and then it becomes part and parcel of our all activity in the nuclear plant operation. That is risk conscious monitoring, surveillance, procedures, SSC, prioritization, emergency procedures, like that. And the different activities are again listed over here. Identification, how it happens, prioritization, management towards ensuring risk to be as low as measurable parameter and all that. And this thing, they help. One more input is there along because risk based engineering, risk monitor is a part of this thing. So many countries world over, they are having a risk monitor either in the control room or at the back of the control room, so that any action to be taken, what is the how we can map, let's say one component, one diesel generator, you have to take it out of service, and if tech spec says okay, within 3 days it should be returned back to service, but suppose you want 2 additional hours, so it is possible that you can add 2 hours and simulate it on the risk monitor, and you will know that whether there is a risk increase or not. Probably this can be an intervention, and if you submit this thing to a regulator, probably you get a regulatory clearance. This I give you just one example. So if you want to have some additional element that will satisfy the not exactly the printed version of tech spec, but it answers the risk levels, so they can see in conjunction and see that okay, you get the permission, but only the defined period you have to complete the activity, otherwise you shut down the plant. So you are not violating the tech spec, you have met the regulator and you got a risk informed approach used in the plant in the support of decision making. Now, as I mentioned, human factor model in ARCOM is, as I come to the CQB, because most of the things we have discussed over here, human is a major contributing factor. That's why it needs attention. That's why we have simulators in the plant. That's why we have, all of you should know that for a nuclear plant, after doing your BTech, the training goes on almost 3+ years, 3+ years, then only you get an authorization. The kind of attention that you get in training before you are authorized for the control room, even then you have one senior person, and so these are the you can say conservative approach that we are using, because human factor is so important for the plant safety. Most of the available human reliability model essentially long with the window, and so the time window and all, they make the difference, because if you have to do a job in a time window given which is not sufficient, then the chances of error are more. So that kind of provision can be judged in a simulator room, or direct data on the plant procedures and all that, but that should be satisfied. Okay, and the additional element is the safety risk, the security risk is again it is forming. So probably as of now, security risk is not part of the simulator, but then it is becoming slowly, security risk is becoming part and parcel of operation and maintenance culture. Already regulatory guides are available, procedures are available. So, okay, so this has to be translated into computerized procedures. Most of the available model of the plant have direct provision on risk-based engineering phase, conscience. So conscience is a factor which takes care of the security risk. To begin with, we either say 0 or 1. If a conscience is intact, then we put 1. If it otherwise it is 0. So it is not part of that model. I'll show you in CQB model how it is estimated. So, but if we have a matrix where conscience of individual can be characterized from 0 to 1, then it becomes easier to take care of and address the security issue also. Therefore, RB risk-based engineering RISCOM have a CQB model. There is a consideration of consciousness. So CQB, I will be telling you what is CQB: consciousness, cognition, and conscience playing out at the level of brain. So B stands for brain. 3C are for consciousness, cognition, and conscience. So cube, C cube. Actually, it is cube like we write an exponent, and this provides the answer. And this model validation is going on. Human prognostics is being investigated as future R&D. This thing, So here this is summary actually. Human prognostics. Now, when we say that human is so important in all that, how we ensure on perpetual basis that human health or psychology is not affecting the plant. Okay, so so this is a matter of R&D that has to be done, because human is a very important factor. But one thing is sure, that the kind of training and rigorous training procedures and all that in India that we have, human errors are less compared to the database value that what we have here is. So that reliance, then we have simulator for all nuclear power plants, simulator for even research data also. So our advancements are keeping a pace. So this is the CQB model here. You can see the 3 factor: consciousness, cognition, and conscience. So what is human? We are defining here. We interact with the internal bases: eye, ear, nose, mouth, body, mind. And then at human level, it gets converted into conscious seeing, conscious listening, conscious smelling, conscious speech, conscious sensation, and conscious analysis. Mind deals with the analysis. So these are called the stimuli. And how we interact, these things, their formation happens: external visible form, sound, odor, this thing. These are the things which come to use. Stimuli is generated, brain forms a perception, and then conscious is an intervening factor, and that's how the action follows. So that means I have taken care of security aspect along with the random aspect also. And then it goes through this, and the formation occurs, and the consciousness generated. So in CQB model, the consciousness has been considered or postulated to be fundamental to the human existence, and cognition operates. Efficiency of cognition depends on consciousness level, and the sense spaces are operating through this. And then finally, this model is CQB. Probably this model operates by stress ratio. What is the stress ratio for a given context? So is equal to 1 minus CS, consciousness has been, and 1 minus P0, where in P0 probability of failure, cognition has been captured. So P0 is nothing but during normal time, what is the probability of the subject failure, human failure. And the ratio of stress to one training or context driven factor will give you answer probability of failure for given stress ratio. So this model operates on stress ratio rather than time, because other than time there can be many factors which can affect the human performance. It could be humidity, it could be high temperature, it will say so many things. The person is loaded with information during a situation, so like that.